So the last thing we did, recap, was finding the empirical formula from percent composition. So the 3 steps for that was number 1, we picked a sample size. So what's the easiest sample size when you're dealing with percents? 100 grams. You picked 100 grams sample size, and you use that to determine how many grams of each element. Step 2, we take those grams of each element and convert them to what? Moles. Convert to moles. How do you convert from grams to moles? Molar mass. Divide or multiply? Divide. Good. We divide by the molar mass. And then step 3, once we had moles of both, but they weren't pretty whole numbers, what did we do?
Divide by the smallest.
Good. Divide by the smallest, which is the same thing we did in lab last week. Divide by the smallest number to get to whole numbers. So those were the 3 steps we had when we were given the percents to get to the empirical formula. Now in this section, we're going to get to the empirical formula a little bit differently, but some of these steps are still going to be the same. So that's why I wanted to recap these steps before we move on. Combustion analysis. So what does combustion mean? What is that reaction? Burning. We're going to burn it, right? So combustion analysis means I have some compound, I don't know what it is, I'm going to burn it to find out what it is, which sounds kind of silly at first, but it actually does work. So when we burn it, we have some sort of a hydrocarbon, which is a compound containing what? Carbon, and hydro means not water, but hydrogen. What element? Hydrogen. So it contains carbon, hydrogen, possibly oxygen. We saw the one with butyric acid earlier this chapter. And then it reacts with what? What else does fire need to burn? Oxygen. Good. So they react with oxygen, and they produce what 2 products? Does anybody remember what they were? CO2 and water. Good. CO2 and water. So the 3 elements present are oxygen, carbon, and hydrogen. So if I know how much oxygen, carbon, and hydrogen are in there, then I can convert that to moles and figure out what the molar ratio was in my original compound. So here's what this looks like. I have some sort of a sample that contains carbon, hydrogen, possibly oxygen. I'm going to burn it. As I burn it, we're going to pump in oxygen. We're going to burn it until the sample is completely combusted, completely gone, nothing is left. Now it's going to go through a series of filters. This filter right here is a water absorber, and then the second filter is a carbon dioxide filter. So 100% of the mass of my sample is gone at the end of the combustion, and I end up with hydrogen, or with all of the hydrogen from my sample over here in the water, all the carbon from the sample over here in the carbon dioxide. Now oxygen is a little bit tricky because oxygen is in everything. It's potentially in the sample, may not be, but it's being pumped in the inlet here, and it ends up both in water and carbon dioxide. So I'll show you a little bit how to get to how much oxygen there is. But every gram of carbon that was in my sample ends up in the carbon dioxide. Every gram of hydrogen that was in my sample ends up in the water. Yes?
What are those places?
They're filters. The first one was copper oxide. They don't tell us what the second 2 filters are, so I'm not quite sure what they are. Alright, so let's look at a compound that contains carbon, hydrogen, and oxygen. So this is a familiar compound. It is glucose. So what do we have glucose for? Sugar, right? It's the sugar in our bloodstream. So glucose is a hydrocarbon. It contains carbon, hydrogen, and it also contains oxygen. We can burn it. You can burn sugar, right? So let's look at a reaction that we're going to pretend we don't know what the formula is for glucose. So with these problems, when you're doing homework problems and sample problems, it's usually going to tell you the word problem, what the compound is. So you're going to be tempted on the homework to look up, well, what is the formula of glucose? Don't do that. It might help you when you're doing the homework, but on the test, I'm not going to tell you what the compound is, and even if I did, you won't have Google on the test. So make sure you go through the steps when you're practicing this out on the homework. So let's try this out. Suppose, and this example problem is on page 100, suppose that in one such experiment, the combustion of 18.8 grams of glucose produced 27.6 grams of carbon dioxide and 11.3 grams of water. We want to know what is the empirical formula of glucose from this. So I'm going to start a new slide. So we have room to work this out. So those numbers again were 18.8 grams of glucose, reacts to form, so glucose, we're going to pretend we don't know what the formula is, we just know it contains carbon, hydrogen, and oxygen in some ratio. When it combusts, what's it going to react with? That's the products, but what is it going to react with? What's the other reactant? Oxygen, good. So I'm going to write an equation here. I'm going to react with oxygen, and then the products are CO2 and water. And they've told us the masses of those. 27.6 grams of CO2 and 11.3 grams of water. And the question is, what is the empirical formula for glucose? So at this point, I've had students in the past go, well, wait a minute, mass wasn't conserved. How did you end up with more mass than you started with? And what is the answer there?
Oxygen.
Oxygen, good. We don't know what our mass of oxygen going in. Oxygen's in the air. We can't control that. So that's why you can't go by conservation of mass to determine what the mass of the oxygen is. But we can use it to determine the mass of carbon, because every gram of carbon here ends up there. Every gram of hydrogen here ends up there. So the idea is, if I can determine how many grams of carbon are in carbon dioxide, then I'll know how many grams were in glucose. If I can determine how many grams of hydrogen were in water, I can determine how many grams were in glucose. And then I'm at the point, step 2, that I was in the last problem. I have grams of my elements, convert to moles, divide by the smallest number. So, same idea, just the first step is a little bit different because we can't pick our sample size, we have to use the sample size we were given. Yes?
Where did you say you got a CH?
We just know that it's a hydrocarbon. Yeah. So we don't know what those ratios are. That's why I put little question marks.
You're talking about glucose. Is that 100?
Yeah, we're assuming we don't know what the formula is for glucose. Yeah. So we have, let's start with carbon dioxide. Change color here. We have 27.6 grams of carbon dioxide. Now there's two different ways of doing this. The first way is the way your book does it, and it says, okay, I want grams of carbon dioxide turned into just grams of carbon. We can do this by converting this to moles, using the molar ratio of carbon to carbon dioxide, and then converting back to grams. So that's the way the book does it. We'll do it that way, and next time I'll show you a different way that some students prefer. So first step, how do I convert grams to moles? Multiply or divide? Divide, good. Don't get mixed up. Divide by molar mass. So, molar mass of carbon dioxide. How do I find that? Good. Add up the masses of the elements. So, a carbon is 12.01. Each oxygen is 16. So, that is 14.01 grams per mole. Right. No, can't. Erase that because I did it wrong. Now you're not going to let me erase it, are you? We'll just change colors now. So 44.01. 44.01 grams per mole. Okay. Everybody see the 44? All right. That gives us how many moles of carbon dioxide? Good. 0.627 moles of CO2. So if that's how many moles of CO2, what is the ratio for carbon to carbon dioxide? How many carbons is in every carbon dioxide? 1. There's 1 carbon for every carbon dioxide. So we're going to multiply that by a ratio of 1 carbon to every 1 carbon dioxide. And now we have 0.627 moles of carbon. How do we then get moles back to grams? Good, multiplied by the molar mass. So am I multiplying by that 44 again? No, because now I'm just what? Carbon. So I'm just going to multiply by the mass of carbon, 12.01 grams per mole. And we now know that we have 7.530 grams of carbon. So of those 18.8 grams, we now know 7.53 is carbon. Ready to do the same thing to find hydrogen? So with hydrogen, I'm going to start with which compound? H2O. So I have 11.3 grams of H2O. What's the molar mass of water? 18.02 grams per mole. Gives us 627 moles of water. Now when we do its ratio, what element are we going to put on the top? 2 hydrogens, and on the bottom? Good, 1 H2O, because there are 2 hydrogens in every water. So here's where the number gets different. So 0.627 times 2 is 1.25. And what is my unit now? Moles of hydrogen, good. Multiply that by the molar mass of hydrogen, which is good. And that gives us 1.26 grams of hydrogen. So back to our glucose, 1.26 grams is hydrogen. So like I said earlier, you can't figure out oxygen using this idea because we don't know how many oxygen went into the formula. Plus it's in both compounds in the end, so that's complicated. But looking at our starting sample size, is there another way we can figure out how many grams of oxygen are there?
Just subtract those.
Good. Subtract the 2 elements we know from the total sample. So 18.8 minus 7.3 minus 1.26 is 10.01. So if I have 10.01 grams left over, what element must they be? Oxygen. Good. If I have 18.8 grams of my sample and I've determined 7.53 must be carbon and 1.26 must be hydrogen, if I subtract these two from 18.8, so 18.8 minus the 7.53 minus the 1.26, that leaves me with 10.01 leftover grams. That must be oxygen. Start a fresh slide. Those numbers again were 7.53 grams of carbon, 1.26 grams of hydrogen, and 10.01 grams of oxygen. So at this point, I'm in the same place I was after step 1 and the start of step 2 of the last problem. I have grams of my element. What do I do now to get to the empirical formula? What's the next step? Divide by their molar masses to get them all to what? Turn all these grams into what unit? Moles. Good. So molar mass of carbon, 12.1. Molar mass of hydrogen, 1.008. Molar mass of oxygen, 16. Divide by what? What's the last step? Because these aren't whole numbers. Good. Divide by the smallest number. So out of these three, the smallest number is 0.626. So if I divide them each by that 0.626, approximately 1 oxygen, approximately how many carbons? 1. Pretty close to 1 carbon, and how many hydrogens? 2 hydrogens, which means what is the empirical formula? CH2O. There's our empirical formula. Questions about any of those steps? Again, that problem is also on page 100. So this is the empirical formula. Does that mean that's also the molecular formula? Not necessarily. So what's the difference between molecular and empirical formulas?
Ratio.
Simplest form. This is the simplest form, meaning it might have been divided by a number. So this is just the ratio, 1 to 2 to 1. It could be actually 2 to 4 to 2. We don't know.
6 to 6.
Exactly. So, but we need, in order to get from the empirical formula back to the molecular formula, we need one more piece of information, and that is the molar mass of the starting compound. So if we're given that, we can find it. So let's say we're told that. So let's say, given that the molar mass, remember molar mass is big curly M, is equal to 180 grams per mole. What is the molecular formula? About it for a little while. The mass of the entire compound is 180. Then what was the original molecular formula if we know this is the ratio? Figure out the math for that one.
Multiply by 6. Multiply by 6.
How'd you get that?
You add the molecular formula of the original formula and you divide it by the molar mass of the empirical.
Perfect. Find the molar formula of the empirical. So the molar formula of this, I have a carbon, 2 hydrogens, and an oxygen. So that's molar formula. If I add up 12.01 plus 2 times 1.008 plus 16 gives us approximately what as its molar formula, molar mass? About what is the mass of this empirical formula? 30, pretty close to 30 grams per mole. So if our total mass is 180, and each time I have that formula, it's going to count for 30. If I take 180 and divide by 30, that gives me what is a ratio? 6, which means that my empirical formula, I need to multiply that through by 6. So if I distribute the 6, that gives me what is the formula for glucose? C6H12O6, and that is the molecular formula for glucose.
And would you ever get a number that's divisible even?
Yep, in which case the empirical formula and molecular formula are the same.
So it would never be decimal. A 6 never would be decimal.
If that happened, though, these numbers should always be divisible equal to a whole number. If it's not a whole number, that means something went wrong. No, it should either give you 1, 2, 3, 4. It should be a whole number. If it's nothing close to a whole number, something went wrong. Want to try another example? Yes. Yeah. This is kind of one of the longer problems. It just has a lot of steps. Just practice it a couple of times, work through it step by step. If you like it, the way I do it is I write out what I generally do in each step. That's what I did at the very beginning of the lecture, was say, okay, what were the 3 steps we did for the last problem? So describe yourself and give yourself a little checklist. Like you're writing yourself directions to go to somebody's house. You say, turn left on this street, drive 2 miles, then do this. Do the same thing. Write yourself a checklist, a direction list for how to work through this problem. First thing you should do is to convert the grams of carbon dioxide to moles, and so and so and so and so. And then you can work through your directions every time you work out these kind of problems. Until it gets to the point where, just like eventually, hopefully you'll learn the route by heart to your friend's house, you'll get to the point where you know how to work out these problems without having to read the directions each time. Make sense? All right, let's try another example. The combustion of a 5.5 gram sample of benzene produces 18.59 grams of carbon dioxide and 3.81 grams of water. Determine the empirical formula and the molecular formula of benzene, given that its molar mass is approximately 78 grams per mole. And this sample problem is on page 100, but I'll give you a couple minutes to copy those down. Grams of benzene, so benzene's a hydrocarbon. Carbon, hydrogen may or may not have oxygen. Reacts with what in combustion analysis? Oxygen, good. And produces what? Carbon dioxide and water. And in this problem we're told that we produced, what did you do? 18.59 grams of carbon dioxide and 3.81 grams of water. So what was our first step in the last problem? Convert what? Grams to moles of what? CO2. Okay, so let's start with that. 18.59 grams CO2. How do we convert that to moles? Good. What's the molar mass for carbon dioxide? 44.01 grams per mole. Good thing about this is it's always going to be carbon dioxide and water, so you're going to use the same molar masses each time, so you won't have to recalculate them each time if you remember what they are. So grams cancel, we're left with moles of carbon dioxide. .422 moles CO2. Next step, I want to get moles of carbon dioxide to moles of just what? Carbon. So what's the ratio I multiply by? 1 carbon to 1 CO2. And now I have just moles of carbon. Same thing. Now multiply that by the molar mass of just the carbon, which is 12.01 grams per mole, and that will give me grams of carbon. .07 grams of carbon. So now we know of those 5.5 grams of benzene, 5.07 of that is carbon, so it's mostly carbon. Let's keep working and figure out how much of it's hydrogen and oxygen. So how do we figure out how much is hydrogen? Same way, but starting with what compound? H2O. 3.81 grams of H2O. Divide by the molar mass. What's the molar mass for water? Good. Now that I have moles of water, what do I do with that? Multiply by. So what's my ratio going to be? 2 hydrogens to 1 water. That's going to give me 0.42223. Yeah. 23 moles of hydrogen. Last step, how do I get moles of hydrogen to grams of hydrogen? Times 1.008, which is the molar mass of hydrogen. Good. 0.42. I'm going to do 426. It doesn't matter if you're rounding slightly different because we're looking for whole numbers at the end anyways. These are grams of hydrogen. So back to our sample of those 5.5 grams, 5.07 is carbon, and 0.426 grams is hydrogen. So now how do we figure out oxygen? Good, subtract from the 5.5 grams, so 5.5 minus 5.07 minus 0.426 gives me 0.004. There's no oxygen, so that's probably just a little bit of rounding error, 0.004. So that must mean when you add these two numbers together and round, you get 5.5. So that must mean there's just no oxygen in this compound. That's all right. You can do combustion analysis with hydrocarbons that contain oxygen or ones that don't contain oxygen. Benzene apparently doesn't contain oxygen. Yes?
I have a question. When you times 2.11 times 2, it's 422.
I'm getting, well, I had this not rounded, so I had point 2114317 times 2 gave me 0.426. No, so 0.4286. So it rounded. But again, we're looking for a whole number, so little rounding errors here and there aren't going to make a difference in the end. Yeah. All right. So now that I have grams of each, and I don't have to worry about oxygen, here's a neat thing. The first step, once I have grams, is to do what with them? Convert them to moles. Do I already know what the moles are for each of these?
Yes.
Yeah, I already did that on the problem. Right there. I have 0.422 moles of carbon and 0.423 moles of hydrogen. So looking at that, do we even have to divide by the smallest to figure out what that ratio is? It's pretty close to 1 to 1. That's a 1 to 1 ratio. Which means, what is the empirical formula? Good. It's just CH. The empirical formula is just CH. Last part, it did give us the molar mass to be 78 grams per mole. So figure out from that what the molecular formula is. Have you figured out the ratio yet? 6, good. So the empirical formula mass is approximately 13. So 78 divided by 13 gives us a ratio of 6, which means what is the actual molecular formula? Good. C6H6, which is in fact the molecular formula for benzene. Yay! And that's combustion analysis. Next section, this is starting on page 102. Section 6, calculations with balanced chemical reactions. So in the last lecture, we learned how to balance chemical reactions. Now we're going to treat those as a recipe. So what do we use recipes for? To cook things, right? We have ingredients that go in, and hopefully we are producing something. So chemical equations are the same ideas. They're recipes. But if I am doing a recipe and I need to say I have a recipe that makes 1 loaf of bread and I need to make 3 loaves of bread, can I calculate how much of each ingredient do I need? Yeah, so we're going to do the same thing here. We have a recipe for how to make a product, and we're going to try and figure out either how much we can produce with a different starting amount of reactants or how much reactants we need to produce a different amount of product. That's all we're doing. These chemical reactions are just recipes. So first of all, let's look at a simple balanced equation. 2 carbon monoxides plus an oxygen makes 2 carbon dioxides. So here's back to our little ball and stick figures. We have the black ones are the carbons, the red ones are the oxygens. So I have 2 molecules of carbon dioxide, 1 molecule of oxygen, 2 molecules of carbon dioxide. Is this equation balanced? Yes, I have the same number of carbons at the start and the end and the same number of oxygens at the start and the end. It's already a balanced equation. Now, when we were talking about finding empirical formulas from the percent composition in the last lecture, we used this handy idea that it's not just in that formula, it's not just the ratio of the atoms, but also the ratio of the moles. Remember? That's why when we divided to get to the moles, then I said, okay, it's the same ratio. We're going to use the same idea here. This is not just the ratio of molecules, this is also the ratio of moles. And we're talking about ratios here. So for every 2 carbon dioxides, it takes 2 carbon monoxides. For every 2 carbon dioxides, it takes 1 mole of oxygens. Why is it helpful to know that this stuff in terms of moles instead of just molecules? Because I can get to moles from what? grams. If I'm measuring something out in the lab, or I'm doing this in the industry and I'm trying to make carbon dioxide for some reason, like we don't make enough, then I need to know how many grams of each reactant to put into the reactor. So if I can get those grams to moles and look at my recipe, same idea. So we're going to call these stoichiometry and stoichiometric ratios. Stoichiometric ratio means in my balanced equation, what is the ratio between two species? So for example, 2 moles of carbon monoxide in this reaction are stoichiometrically equivalent to 2 moles of CO2, which means I can use this as a ratio. Just like in the last problem, we use the ratio of 2 hydrogens to every H2O. Same idea here, we can use these as ratios to go in between species in the same chemical reaction. So let's look at what I mean. We can write these as ratios. So 2 moles of carbon dioxide to 2 moles of CO2, or carbon monoxide to CO2. Or that would simplify down to 1 to 1 if we wanted to. We could also flip this so it has carbon dioxide at the top. Why might we flip that? Well, let's think back to chapter 1, factor label method. When we had any sort of conversion factor, we always showed it as both directions, one on the top, one on the bottom. How do you determine which one needs to go on the bottom? Whatever unit you started with needs to go to the bottom, so it will do what? Cancel. Perfect. So that's how you determine which way you need it. Whatever unit you started with, if I started with carbon dioxide, I would need this one. If I started with carbon monoxide, I would need this one. So you're going to multiply by the stoichiometric ratio, sometimes also called molar ratios, so that it cancels the unit you started with and leaves you with whichever species you're looking for. So let's try this. Consider the reaction of 3.82 moles of carbon monoxide to form carbon dioxide. So I want to know how much carbon dioxide I can make from 3.82 moles of carbon monoxide. So 3.82 moles of carbon monoxide, and the ratio I would have carbon monoxide drops to the bottom so that it will cancel. My ratio was 1 to 1, so I get moles of carbon dioxide. Now what if I say, okay, that's fine, but I want to know how much oxygen I also need to put into that reactor. So oxygen, let's look at our equation here. What's the ratio between carbon monoxide and oxygen? 2 to 1. Good. 2 carbon monoxides to 1 oxygen. So when I do that conversion, again, carbon monoxide drops to the bottom, so it'll cancel. 1 oxygen to every 2 carbon monoxides, it would require 1.91 moles of oxygen. So that is multiplying by the stoichiometric ratio to get from one thing in the equation to the other. You can go between a reactant and a product back to a reactant, between 2 reactants like we just did here, or between 2 products if you had multiple products. As long as they're in the same balanced equation, you can use the stoichiometric ratio to convert from one thing to the other. The key is you must be in units of moles. This will not work if you're in grams. That's the one big thing. You must be in moles. Questions? All right, let's try this out. Urea. Urea can be synthesized in the lab from ammonia and carbon dioxide according to the following equation. 2 moles of ammonia plus 1 mole of carbon dioxide makes 1 mole of, this is urea, and 1 mole of water. The question is, calculate the amount of urea that will be produced by the complete reaction of 5.25 moles of ammonia. Moles of ammonia.
It's 2 to 1.
So when I put my ratio, what's going to go on top? You can just say urea if you don't want to count it off.
Yeah.
The urea, this is urea. How many ureas? 1. There's an understood 1 here. So 1, I'm also going to just write urea for fun. Urea. And on the bottom, what would go? 2 NH3s. NH3. So, what cancels? NH NH3s cancel, and I'm left with what? Over half that is. Someone grab a calculator. 2.669?
625.
Let's do 625. We'll just do 2.63. And what's my unit now?
Moles,
Urea. We'll just write urea. And this problem is on page 103. So that's easy. One step. Multiply by the stoichiometric ratio. Not so bad, right?
and that would be the same for B.
Yeah. Part B says determine stoichiometric amount of carbon dioxide required. So carbon dioxide to ammonia is a what to what ratio? 2 to 1 again. So that one would end up being the same. 2 to 1 again. That makes sense?
I think it's easier for me to put 5.25 over X and then times 1, because that's what you're
Write it out as a ratio. So like this.
Because, we learn in like
5.25
cross multiply.
moles of ammonia over, we don't know how many moles of urea, is equivalent to the ratio of 2 moles of ammonia to every 1 mole of urea, and then cross multiply to solve for x.
2x divided by 5.25.
Yeah. So if you cross multiply, you get 2x is equal to 5.25 times 1.
I've been doing that for all these problems as well.
So x would be equal to 5.25 divided by 2, or 2 point, say it was 3. Yeah. That makes more sense? Definitely. Feeling good now about stoichiometric ratios. Now, that's just a one step. The problem is, if I'm in the lab, I'm not going to be measuring out my urea and my ammonia in moles. What will I be measuring it in? Grams. Am I stuck in the water, or am I pretty good about converting between grams and moles by now? Well, hopefully I am. Are you guys? We've been doing it all chapter. We could do it, right? Convert between grams and moles, moles and grams. Let's try that. All right. Nitrous oxide. What do we use nitrous oxide for? Laughing gas, or, car racing. It's typically used as an anesthetic in dentistry. It's manufactured by heating ammonium nitrate. So this right here is ammonium nitrate. Those are both polyatomic ions. Again, hopefully you remember how to go from names to formulas. Ammonium is NH4, nitrate is NO3. So that's the solid. What does this little triangle mean? Heat. So we're heating this up. So I'm heating ammonium nitrate. I produce nitrous oxide and water. So there's my balanced, already nice and balanced chemical equation.
1 to 1.
Yeah. So the stoichiometric ratios is for every 1 ammonium nitrate, you make 1 nitrous oxide, or for every 1 ammonium nitrate, you make 2 waters. There's our stoichiometric ratios. Question is, calculate the mass, not moles, of ammonium nitrate that must be heated in order to produce 10 grams of nitrous oxide. So I'm not giving you moles. Can you use stoichiometric ratios in grams? No, I said earlier, disclaimer, you must be in what unit before you use the ratio? Moles. Can we get to moles? Yes. So what's our starting amount here for part A? First step is convert to moles. Convert what to moles? 10 grams of nitrous oxide. So I'm going to write 10.0 grams of N2O. How do I get that to moles? What with the molar mass? Divide. Good. Divide by the molar mass. So molar mass of nitrous oxide, I have 2 nitrogens at 14.01 apiece plus 1 oxygen at 16 is a mass of what?
44.02.
Good. 44.02 grams per mole. grams divided by 44.02 gives me what number?
227
0.227, and what is my unit now?
grams
So, alright, grams are on top, grams are on the bottom, they cancel. Moles are in the denominator, which makes them come up to the numerator. Moles. Moles of what? Good. Nitrous oxide, N2O. So now I'm at the starting point I was in the last problem. I'm at moles of one thing, I want to get to the other thing. So what did I do now? Good. Use the stoichiometric ratio. So my stoichiometric ratio is going to have 1 on top.
That's 1 to 1.
But what species on top?
Ammonium nitrate.
Ammonium nitrate is what you want. I want ammonium nitrate, so that's what's going to go on top. So ammonium nitrate is NH4NO3. 4NO3. And what species goes on the bottom? What? Nitrous oxide. Whatever I have drops to the bottom so that it can do what? Cancel. Good. So what is this ratio? 1 to 1. So 1 over 1. 0.227 moles of ammonium nitrate. NH4NO3. We'll do part B on a different page, so I can just write it over here. So last step, it doesn't want the moles of ammonium nitrate, it wants the what of it? The mass. So how do I get these moles to mass? Good, multiply by the molar mass of ammonium nitrate. So we have to add up the mass of this whole thing. I have 2 nitrogens at 14.01 apiece. I have 4 hydrogens at 1.008 apiece. And I have 3 oxygens at 16 apiece. So that's 80.05 too. When we do this, moles will cancel. We'll be left with grams. We've got 3 significant figures. How many grams of ammonium nitrate? 18.2. 2 grams of ammonium nitrate.
It's probably late in the game for the questions. But why is there an N over there and there? Just to show that 2 compounds went together?
Good question. Because this is an ionic compound, so ionic compounds are always written as the cation,
Oh.
followed by the anion. So the cation is NH4 plus ammonium, and the anion is nitrate, NO3 minus.
Alright, sorry.
Yeah, but it's 2 separate components, just like sodium and chlorine and sodium chloride. They're just polyatomics. So if the last problem just took 1 step, how many steps did this problem take? I had to get from grams to moles, that was step 1. Step 2 was the same as the last problem, multiplied by that stoichiometric ratio. And then the third step was getting back to grams. 3 steps. So we're writing ourselves directions to get to somebody's house, and it's only 3 turns. Can we make it there? Hopefully.
Depends on how the other drivers are.
Depends on the other drivers, depends on if the road is flooded. Turn around, don't drown. So let's summarize that. Everybody have this copy down? No. All right. Okay. Add to the page. So these problems are called stoichiometry problems. And it takes 3 steps to solve them. It would help if I would turn the pen back on. So I'm going to call this 3 simple steps to stoichiometry. have younger siblings that likes the little secret ancient Oso bear? Anybody know what I'm talking about? My kids love that show. The little bear who goes and helps little kids learn how to tie their shoes and brush their teeth. But this little theme song is always solved in 3 special steps. 3 special steps. Yeah, that song gets me every time that I do this lesson. I want to start singing it because my kids love that show. 3 special steps. That's all you need. Okay, so 3 simple steps. Step number 1. We have grams. What do we want? Moles. What do we want? Moles. So step 1, convert grams to moles. And how do we do that? Good. Divide by molar mass. Now that I have moles, I want to get not to moles of what I started with, but moles of what I ended with. So let's put a little disclaimer here so you can keep track of what we're talking about here. So stoichiometry, this, change colors, is when I want to go from grams of some component X, and I'm asking for grams of some other component Y. So first thing we're going to do is convert grams of whatever X, whatever we started with, to moles of X. So step 2, how do we get from one thing in the equation to another thing in the equation, from X to Y? The molar ratio, or the stoichiometric ratio. Step 2 is to convert from moles of X to moles of Y, whatever you started with to whatever you're being asked for, and you do that by multiplying by the molar ratio. Ratio Y over X, where that is from the balanced equation. 1 to 1, 1 to 2, 2 over 1, whatever those ratios was for the balanced equation. Equation. So last step, I'm at moles of Y. What do I want to do with that? Get to grams. Last step. Convert moles of Y to grams of Y. And how do we do that? Good. Those were the 3 simple steps. Yes?
What do X and Y stand for?
They're just 2 things in the equation. So like in the last problem, in this last problem, I was given nitrous oxide, so nitrous oxide would be my X. And I was being asked for ammonium nitrate, so ammonium nitrate would be my Y. It's just whatever 2 things in the equation you're going between. Starting here, going there.
Okay, so X is what you start with and Y is what you're trying to get.
Good, yes. X is what you start with, Y is what you're trying to get to. Alright, feel like we can follow those 3 steps? Alright, so we've got one more section in chapter 3, and that is limiting reactants, so we'll cover that in the next lecture. Let's go ahead and take a break before lab.